Good day and welcome to learning exercise 8.1. Now in topic 8 we're looking at differential calculus. Right? And first I'm looking at rate of change and tangents. Now you should know that differential calculus is one of the most important topics in maths, included with integration and later on partial differentiation. But in a nutshell, differential calculus revolves around rate of change. As Einstein says, the only thing that's constant is change. Differential calculus allows us to see how quickly this change would take place, and that's basically how we look at it. We want to see how one variable affects another one, etc. Mathematically, we can say rate of change is equivalent to a gradient of a graph. So along the way, you will see when you look at rate of change calculus, we're actually finding different types of gradients. Now to strengthen this concept, let's look at a linear function. Here I'm looking specifically at y equal to 3x plus 6. And there if I draw it, that is what I end up with, a straight line. So they have a point minus 2 and 0, minus 1 and 3. They have 0 and 6. I can go further to 2 and 12. Right? Now, to calculate the gradient by now you should know it's change in y over change in x, y2 minus y1. So there I'm looking at 0 and 6 and minus 1 and 3. That's 6 minus 3, and that becomes at 0 minus 1, or 0 minus minus 1. 6 minus 3 is 3. 3 divided by positive 1 give me 3. Same when I calculate the gradient at 6 and 0 and negative 2. So there you see 6 and 0 and 0 or minus 2 and 0. If I substitute in there, I get 3 as well. So you should note with a straight line, no matter where we go, we can be seen that gradient stays constant, and we say my rate of change is constant. So linear function gives a constant rate of change. Right? Quadratic function, I'm looking straight out at y equal to x squared minus 1. That's a graph there. If we differentiate difference of two squares, I end up with minus 1 or plus 1 parabola. Again, we should be able to see the gradient is not constant. It is constantly changing. So gradient at that point would not be the same as gradient is there, wouldn't be the same as the gradient there, gradient there. So that leaves two options open to us. Either we calculate the average gradient between 2 points on the graph. So we select two different points on the graph and we calculate the average gradient. Or we find the gradient of a tangent at one point. Alright? So you will see what is a tangent, and should have been introduced to it before in trigonometry, etc. So average gradient, again, is change in y, change over x, y2 minus y1. And we have this notation where we say fx plus h minus fx over h. So we take what's fx, add something to it. Alright? So I'm going to specifically look at this concept of average gradient. So we go over the same function. Now I'm looking at some points. There I have 4 and 7. Turning point of that function or this function is 0 and minus 9. Alright, they have a point 3 and 0. You have 2 and minus 5. So if I look at average gradient between 4 and 7 and 0 and negative 9, I can write it and use that format, average gradient. Or I can say f4 minus f0 if I use fx plus h minus fx. So there, y2, as you can see, 7 minus minus 9, 4 minus 0. That gives me 16 over 4, which gives me a gradient of 4. If I go this way, f of 4 gives me 7, f of 0 gives me negative 9. So 7 minus minus 9, which 4 over 0, which then gives me 4. So as you can see there, between 4 and 7 and 0 and 9, the gradient there is 4. If I go to the next point there, 3 and 0 and negative 9, if I calculate average gradient between those 2 points, my2, or average gradient, the format, substitute the points in. By now you should know how to do that. See there, I get 3 and 3. So basically what you should note, at 4 and 7 my gradient was 4, at 3 and 0 my gradient was 3, and as I move closer towards this point, what is taking place? So as I move closer from 4 and 7 and shift closer to 0 and negative 9, the gradient tends to 0, meaning the gradient will eventually go down till gradient equals 0. Right? So the gradient of a tangent to the curve is the gradients of various lines as they get closer to that point. So what I've done there, as I moved everything closer to 0 and 9, right, eventually I end up with a tangent. Now as you can see here, the tangent is simply a line that touches another graph only at one point. So if I draw a straight line and it touches a parabola at one point, that point there where it touches, and the line itself then is referred to as a tangent. So the gradient at points 0 and 9, fx approximately that. Process of getting this h when I subtract the two x values is h. Closer to 0 is actually known as taking the limit. Alright? So we can rewrite this and say gradient at points 0 and 9 equal the limit of h tends to 0, fx plus h minus fx and h. So this allows me to find the exact gradient for that specific curve, and therefore then see what rate of change took place. Alright? Per definition, we say this is the definition of the first derivative. Yeah, it's just first notation, f dash x, or first derivative of x, equals the limit as h tends to 0. Remember, we process of moving something towards 0. Fx plus h minus fx over h. The first derivative of function is the gradient, rate of change of that function at any point on a curved graph. Right? This equation will also be used when we have to find the first derivative using first principle. So first principle is effectively your first exam question under differential calculus, and in the next lesson or lessons that follow we will look at the first principle. All the best. God bless.